Compared to thermal IR sensors, quantum sensors detect photons and are much more sensitive than sensing heat. Quantum infrared sensors represent the cutting edge of IR sensor technology. They are wavelength dependent and known for their quick response times and high detection accuracy. They require periodic cooling to ensure precise measurements, making their operation slightly more complex than thermal sensors. Quantum infrared sensors find their use in highly specialized applications, such as spectroscopy, where they help identify different materials based on their infrared signatures. Astronomers also use them to detect celestial objects not visible in the regular light spectrum. Only detecting objects in the 3 to 20 micrometers IR range, quantum well IR sensors are limited to mid-IR and far IR bands. Compared to thermal IR sensors, quantum sensors detect photons and are much more sensitive. The signal output of a quantum detector, typically a gallium arsenide (GaAs) semiconductor chip, is very small and easily swamped by noise generated internally to the sensing device at room temperatures. To overcome this problem, quantum sensors are often operated at cryogenic temperatures such as 77 K liquid nitrogen or 4 K liquid helium to minimize the noise. This significantly increases their cost. Consequently, they are only used if high sensitivity, high resolution, and/or short response times are required at a specific wavelength. For really far imaging, NASA's Thermal Infrared Sensor, TIRS, on the Landsat 8 satellite measures land surface temperatures using quantum well infrared photodetectors, QWIPs, to detect long wavelengths of light emitted by the Earth. This quantum IR sensing employs GaAs semiconductor chips that trap electrons in an energy well until the electrons are elevated sufficiently to a higher state by thermal infrared light of a certain wavelength. The measurements help track how land and water are being used on Earth. There are dozens of distant sensors on the market, and as they become more ubiquitous in electronic devices, they continue to get smaller, cheaper, more sophisticated, and more power efficient. The principles laid out here should give you a basis for assessing new sensors as needed.